All right. So it's just about 5 o'clock, so I'll go ahead and at least start getting started. Okay, well, welcome back, day number 2. So we left off the last time with problem 6, and we mentioned that we would do something else with that particular problem, but just dealing with radiation. So we're going to do that now. So before we start problem 7, let's talk about radiation. So we talked about we said there were 3 modes of want to say 3 modes of transportation again. 3 modes of radiation, heat transfer. Good gracious. So conduction, convection, and radiation is number 3. So let's talk about radiation because we haven't done that yet. All right. So radiation is heat transfer through electromagnetic radiation, right? And when we talk about thermal radiation, we're talking about a very specific wavelength of the electromagnetic spectrum. And we'll talk about that in more detail in Unit 5. But for the time being, I wanted to talk about radiation from a surface. So this surface is above absolute zero, so above 0 Kelvin. So this surface TS is above 0 Kelvin, and it's emitting radiation, and we're going to call this E. So E is the emissive power. And the units are really units of flux, so it's watts per meter squared. It would be really nice if the nomenclature was nice and uniform throughout, because when we talk about flux, like heat flux, we use a lowercase q with 2 double primes, and now we just use a capital E or a capital letter with no double primes, but yeah, there you go. So any body that is above absolute zero will emit radiation. And the amount of radiation is going to be given by emissivity. So epsilon times sigma times this EB. So EB is the emissive power of a black body. It's a perfect emitter. It's a perfect absorber, perfect emitter of radiation. So black body. So a black body at a given temperature is going to emit the most radiation possible due to thermal radiation, due to it being at that particular temperature above absolute zero. The emissivity is there to take into account the fact that it's not a black body. Real surfaces, so this is a surface characteristic, and it's for real surfaces, this is something less than 1. But emissivity, emissivity, and like I said, it's anywhere between 0 to 1, 1 being a perfect black body and less than 1 being something not. And then this sigma is the Stefan-Boltzmann constant. Right? And the Stefan-Boltzmann constant, it's a constant. And this is 5.67, 5.67 times 10 to the negative 8 watts per meter squared Kelvin. So it's a constant, but it's not anything that you actually have to memorize, because if you look in your heat transfer packet, that big PDF 41-page behemoth, it actually is on here. So you can see up in the upper left-hand corner there, you've got Fourier's law, which is for conduction, Newton's law, which is for convection, and then you've got the Stefan-Boltzmann law, which is for radiation, and that Stefan-Boltzmann constant is right here. So again, you don't actually have to memorize it, but it's a pretty easy number to memorize, 5, 6, 7, 8. Yeah, so, all right. But there you go. All right, so that's the emissive power. And then we have to take into consideration that other things around our surface are also emitting radiation, and they're bouncing off our surface here. So this we term G. G is the irradiation. Now, not all that irradiation gets absorbed by the surface, but it is coming in. It's incident on the surface. And the units here are watts per meter squared. So when we talk about the net rate of radiation coming off of that surface, or the net flux coming off of that surface, that Q net, and I'm going to put two little double primes to indicate that it's a flux, it would be all the stuff that's coming in, or all the stuff that's being emitted, which is the emissivity times the Stefan-Boltzmann constant times the emissive power of a black body, plus not all of the radiation that is being irradiated onto that surface, but a fraction of it that ends up getting absorbed. So this guy is the absorptivity. And just like the emissivity, it's a number between 0 and 1. A black body, not only is it a perfect emitter, meaning that it's got an emissivity of 1, but it's also a perfect absorber, so it also has an absorptivity of 1. So there you go. We're going to look at a special case. So our special case is that we've got, here's our surface, and it's surrounded by a large enclosure. And that enclosure is at some temperature TSRR. So SURR is surroundings, but it's the surface temperature of the enclosure. This guy is at TS, some temperature TS. And again, yes, this surface is emitting radiation. So there's the emissive power, but you also, because the surrounding enclosure's surfaces are emitting radiation as well, that irradiation is incident on the surface, and a portion of that is going to get absorbed. And your book has an equation for what's called the Q net radiation. Actually, it's a flux term, but it's for this special case. I'm actually going to put a little line here. For a surface within a larger enclosure at T surroundings, SURR. And the equation is, we've got epsilon, so emissivity, times our Stefan-Boltzmann constant, times TS to the fourth minus T surroundings to the fourth. And absolutely, these guys have to be either in Kelvin, if it's an English unit, or I'm sorry, if it's an SI units, or degrees Rankine, right? So it's got to be in absolute temperature units. All right, so if you find yourself multiplying or dividing or raising something to a power, that temperature it needs to be in absolute temperature units. Okay. One assumption that goes with this, yep. That good? One assumption that goes with this is that the absorptivity and the emissivity are equal to one another. And that sort of makes sense. I mean, if you look at this equation and this equation, they kind of look the same, or they look really similar. And it's by making this assumption that the absorptivity and the emissivity are the same. And by doing this, what we're saying is that this is something called a gray surface, G-R-E-Y. We'll talk about a little bit about gray surfaces in Unit 5, but a gray surface, for now, the only thing that we really need to to take into consideration is that the absorptivity and the emissivity are the same. Um, so the question was, should we memorize this equation? And your extremely generous equation sheet actually has that on there. So yeah, so you've got this guy, and then you've got this guy. So I would just, yeah, oh no, that's okay, yeah. So for a gray surface is defined as one in which the properties of that surface are independent of the wavelength of the radiation that is being emitted or is being irradiated on its surface. But for us, the only thing that we need to worry about is that either we're told that it's a gray surface or we have this kind of special case, in which case you've got a surface or something surrounded by a big enclosure, in which case I want you to make that assumption that you have a gray surface. That assumption will be okay to make, meaning that you'll get a minimal error in your analysis as long as the temperature between the surface and the surroundings, T surroundings, is not absolutely huge. So I don't know, a couple of 100 degrees, maybe it's not going to matter too much. So, all right, but anyway. All right, so let's move on. Problem 7. So we have same problem that we had before, where we had the little stick figure guy. So here's our stick figure. He's smiling, sort of. And he loses radiation. It's terrible. Okay. So the surface of his skin is, what was it, 29 degrees? So 29 degrees. The surface area of his skin through which he's losing heat is 1.6 meters squared. And then we also, I think we were also in the previous problem, we were given some, that's right, yeah, we were also given some information about, we were given T infinity, we were given H, and with that information, so 20 degrees, 6 watts per meter squared degrees Celsius. With that information, what we found was that Q by convection, so because of that moving air, the Q by convection was 86.4 watts. Okay. But now our problem statement says a few other things. So it says the person loses heat by radiation as well as convection at the surroundings to the surrounding wall surfaces. So the person is sitting in a room. I probably should have drawn the person a little bit smaller, but that's okay. So he's in a room. Here's our big enclosure. And I know that this guy says TS. Let's actually rename that, not TS, but TSURR, because that's what it is, the surface temperature of the wall. This is 20 degrees. All right. And so we want to figure out the net rate of radiation between those two. First thing I want to do is, I know I've talked about radiation, so I'm probably raising some temperature to a power. So I probably want to go ahead and put this in Kelvin. So 293 Kelvin, surface temperature here. This guy is going to be 302 Kelvin. Okay. And we want to find the net rate of radiation, the net rate of radiation from the person to the wall surfaces. So keep in mind, yes, we have heat transfer via convection. So Q by convection. And then we also have Q by radiation. Okay. So our Q by convection, we've already got that. That's our 86.4 watts. So I'll go ahead and write that. That's not supposed to be a, there we go, 86.4 watts. And then we've got a plus. So the Q radiation, let's go to our equation sheet just so we don't forget. But we're looking at this guy right here. You may notice that this is just a tiny bit different from what we wrote down just a hot second ago because it has an area in the equation, right? So you've got an area here, and that's because before we wrote down the equation for flux. So flux Q double prime is Q divided by area. So that area had gotten divided out in the previous equation. But now we need just need to pay attention to our units. So we do need to have an area in there. So this becomes emissivity times the Stefan-Boltzmann constant times the area, and the area that we're talking about is the area of the little stick figure guy, times TS to the fourth minus T surroundings to the fourth. Right, and that's it. And so we're going to plug in some numbers. So I've got 86.4 watts plus, oh, did they tell us? I know they did. I just didn't write it down. Oh, no, they didn't. I don't think. Yeah. So, yeah, the piece of information that we were kind of missing in the problem statement is this guy. So what we're looking for is the emissivity of skin, of human skin, which is kind of creepy. And that's in actually table A8. You don't actually have table A8 in that little packet. I was trying to be, you know, pick the things that you would, the tables that you would use the most. And A8 was one that we really didn't use that much. But it is in your book, so you can look that up. So in table A8, the emissivity of skin is 0.95. So there we go. All right, so 0.95, and then we've got the Stefan-Boltzmann constant, 5.67 times 10 to the negative 8 watts per meter squared Kelvin. Perfect. And then we've got the area, so 1.6 meters squared, area of the person. And then we've got those two temperatures. So surface temperature of the person was 29 degrees Celsius or 302 Kelvin. That was raised to the fourth, minus the T of the surroundings, 293 Kelvin, raised to the fourth. Whew, that was a lot. And so what we get, this guy right here, if we do the math, hopefully correctly, we end up getting 81.7 watts. So this whole thing, Q net, ends up being 168.1 watts. That's our Q net or Q total or whatever you want to say. So this is the net heat transfer rate coming off of that person due to both convection and radiation and the incident radiation from the surrounding enclosures surfaces. All right. All right, so let's keep on going. All right, so another radiation problem. We've got an overhead 25-meter long uninsulated industrial steam pipe, 100 millimeters in diameter. So I'm going to just draw this to be a little bit fatter here. All right, so here's my room. Okay. And then here's my steam pipe. Oops, don't like that. Like that at all. All right, so there's that guy. And let's see. So they tell us the length of this guy. Oops. Q. Right. So the length of this guy is 25 meters. They tell us the diameter. Good. So our diameter is 100 millimeters or 0.1 meters. Oh, I'm sorry. Like this? They asked me to scroll up for a hot second, so. Okay. All right. All right, so it's the steam pipe is routed through a building whose walls and air are at. Okay. It's the Amazon delivery guy. The dog is sounding the alarm if you can't hear that. So the wall and the air, I'll call this TSURR. So this is 25 degrees Celsius. Try to close a little bit of that out. 25 degrees Celsius or 298 Kelvin. Okay. And the air is also at the same temperature, so 298 Kelvin. All right. And actually that air is also is responsible for some convection here. So they say natural convection. So natural convection. So H is equal to 10 watts per meters squared Kelvin. So when we talk about natural versus forced convection is I turn on the fan and air is moving and the air and whatever surface it's interacting with at a different temperature, there's convective heat transfer that way. Natural.
Is that T infinity?
Yeah, I just thought it would be a good idea to scribble over it even more to make it difficult to see. That's what I decided. Okay. Okay. How's that? Sort of better. So natural convection is due to differences. So somebody said, oh, do I have some sort of, yes, thank you. So Blake, yes, thank you very much. This is K to the fourth. So the units of the Stefan Boltzmann constant, I'm sorry, watts per meter squared, Kelvin to the fourth. And I feel like I've written that incorrectly up here as well. Yes. So there were two places that I wrote it. So make sure that you put that there. But anyway, natural convection is due to differences in the density, right? Hot air rises because it's less dense, cold air sinks because it's more dense. And that's the mechanism of convective heat transfer because there's movement of the fluid in that manner. Typically that results in lower convective heat transfer coefficient, hence the 10 watts per meter squared Kelvin. The surface emissivity of this pipe here, it says it's 0.8. And we want to know what the rate of heat loss is. So I'm going to call this A. Q, and I'm looking for net because clearly I've got radiation and I've got radiation and I've got convection. Okay, and then I want to know what's the annual cost of the heat loss from the line. So I'm going to call this A, B, and I'll just kind of underline some things here, yeah, rather than writing it out. I'll throw an assumption on here, but we'll see if I need to assume anything. All right, so I know that the net radiation or the net rate of radiation is just going to be the sum of all the modes of heat transfer that we've got going on. So I've got Q by convection, and then I've got the net rate of radiation. So I'm going to call this net RAD. Again, that's the net radiation of due to the surface of that pipe emitting radiation, but also absorbed radiation due to the irradiation G coming in onto that surface from the surrounding enclosure. All right, so this is going to be H times A times T of our surface minus T infinity plus, got my emissivity, Stefan-Boltzmann constant with the correct units, the area, and then we've got Ts to the fourth minus T surroundings to the fourth. The area is the surface area of that pipe, right? So surface area of the pipe, and let's go ahead and write that. I'll put that kind of a star over here. So that area would just be the perimeter times the length of the pipe. So ID would be the perimeter, and then times L. So all of this stuff is multiplied by an area, so I'll just put him on the outside. So pi D, 0.1 meter, L, 25 meters, okay, times, all right, and so we've got the convection. So I've got 10 watts per meter squared, Kelvin, times TS. TS, I believe this guy, they told us this guy was, I didn't write that on there, but it's right here. So 150 degrees Celsius. So 150 degrees Celsius minus 25 degrees Celsius, right? Also same as 25 degrees Celsius. I could have converted it to Kelvin, but it doesn't really matter because a delta T in Kelvin is the same as a delta T in degrees Celsius. Okay, so that's the convective term. I'll bring the other one down here so my head doesn't get in the way. So I've got epsilon, the emissivity 0.8 times 5.67 times 10 to the negative 8 times watts, or watts per meter squared Kelvin to the fourth, times TS. So TS, so this would be 423, wouldn't it? 423 Kelvin. All right, so this is going to be 423 Kelvin to the fourth minus 298 to the fourth. All right. Okay. I think I've got all the parentheses there. So when I plug all of that in, I get a value of 18,405 watts. So I'm going to box that guy right there. Perfect. All right, and then we were also supposed to find the annual cost if natural.
Yes, sir.
Yes.
Shouldn't the second half of the equation include area?
I think it's all. Yeah.
Oh,
Yeah. Sorry, I was taking the lazy man's way out. Yeah.
That makes sense. Thank
you.
Yep.
And then the annual cost. So I'm going to use the units just to kind of guide me through the equation. So annual cost of that loss. So 0.02. So 2 cents per megajoule. I know I have 18,405 watts, which is a joule per second. You need to reconcile the joules. So megajoule is 10 million joules. So that's good. Got megajoules, joules. I do not know off the top of my head how many seconds are in a year. but I do know that there's 3,600 seconds in an hour, 24 hours in a day, and 365 days in a year. All right, and so that gives me an annual cost of 11,608. So it would probably behoove them to throw some insulation on that pipe. All right, I think one more radiation problem, and then we'll kind of move on. Leave it there for a hot second. I know I keep on making people need to go back. So. Okie dokie. So I'll keep on moving. All right, so problem 9, we have a spherical interplanetary probe, which I'm going to draw as a lovely circle. All right, so there we go. Super pretty. And the probe has a diameter, I'm going to put D here, 0.5 meters, and it contains electronics that dissipate 150 watts. So, go. So what I'm going to do is I'm going to call this E dot G. So this is my 150 watts. If you recall from last night, we talked about energy balances. So I'm kind of jumping the gun just a hair bit, but so that energy balance we had E dot ST equals E dot in minus E dot out plus E dot G. That's our control, that's a control volume energy balance. Okay, and so if our control volume, let me see if this is too fat. Oh, that's okay. So if our control volume is our sphere here, that the electronics are inside and they're generating heat. So that is a volumetric, or could be counted as a volumetric heat generation term. So that's why I'm using that E dot G. Okay, so then the probe has an emissivity of 0.8. So he's clearly irradiating something. Okay. So this is my Q radiation. Okay. And then the probe does not receive radiation from other surfaces, for example, the sun. So what we're saying is this is not that special case that we were talking about before, where our surface is being irradiated by radiation from other sources, from other sources, from other surfaces. So the question was, what does E dot st stand for again? So this guy is the rate of energy stored. It's analogous if you think back to Thermo 2 or Thermo 1. It's the DEDT term. So if it's steady state, that thing goes away. And in fact, that's what we're going to do in just a hot second. But we want to find the surface temperature because that's something that was not given to us. All right. So yeah, we'll go ahead and assume steady state because I don't really know how things are changing with time anyway. So I think I would like to get rid of him. So again, I'm getting rid of that E.st because things are not changing with time. So I'll make a little note that this is 0 if it's steady state, SS, steady state. All right, and then I look at the diagram that I've drawn up there, and I only have one arrow going out of this thing. There's not anything coming in, it's all going out. So I'm going to get rid of this guy as well, right? So clearly my E dot out is equal to that E dot G. I'm going to bring the E dot G over here actually. Okay. Right. So I know that this is all equal. This is all equal to 150 watts. And then the E dot out is equal to that Q radiation that I drew before. Get that away. There we go. All right. Let's go ahead and oops. Okay. So this is going to be equal to, all right, so I'm going to go back if I forgot what the equation is. Again, it's on your heat transfer packet. So it's going to be this guy right there. So it's all on there. You just have to know where to look. So it's going to be the emissivity times the Stefan Boltzmann constant times the area times that TS to the fourth that we're looking for, because remember that is what we're ultimately looking for, TS. All right, so I just need to plug in some numbers. So TS is going to be equal to, I'm going to have 150 watts on the top, and then I'm going to have the emissivity 0.8 times my Stefan, oh, sorry. Can you explain why E in went away? Just because if I look at my picture here, there's nothing coming in, right? And Kale said, so there's no surrounding temperature. It's not that there's no, it's the fact that there's no convection, convective heat transfer, right? There's no mass out there. It's just a vacuum, right? So there's, yeah. All right. So I've got my emissivity 0.8, then I've got my Stefan Boltzmann constant 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth. Welcome. And then my area, I'm going to put that 150 watts up here. If you're like me, sometimes you forget the simple stuff, and so which is why on your equation sheet, if you look over here, I put some areas and volume, or equations for area and volume, just in case like you've stuffed your head full of all kinds of complicated stuff that you forget the simple stuff, and I don't want that to throw anybody off on a test. So it's on there. So your area, 4 pi r squared for a sphere. I'll put that on here. So my area, I'll make a little note. Area, yes, 4 pi r squared, or just pi d squared. So this is going to be pi times 0.5 meters squared. And of course we need to take all of this to the 1/4 power. All right, so I end up getting 254.7. 254.7 Kelvin. Perfect. Okay. So all of that's been unit, or not unit, but chapter 1. And now we're moving on to chapter 2. Still unit 1, but chapter 2. So let's kind of scooch on over here. Okay. So I got lots of paper here, but chapter 2 goes into Fourier's law in a more general sense. So we've been talking about applying Fourier's law for one-dimensional heat transfer, which is fine, right? Conduction, heat transfer by conduction. So we're kind of going back, just looking at conduction and the general form of Fourier's law. All right. And I'm going to put it in terms of flux, so I just don't have to worry about the area. So yes, it's negative K dt dx if I've got one-dimensional heat transfer. But, you know, in reality, you're going to probably most likely have multiple dimensions that you're going to have to take into consideration, X, Y, and Z if you're in Cartesian coordinates. So I have negative K, and then you've got your little upside down triangle here indicating that you need to take the derivative or the partial derivative of that temperature with respect to X, Y, and Z. So this is going to be negative K dt dx, little unit vector here, plus negative K dt dy, little unit vector there. You see where we're going. And then we've got a dt, or partial of t, oops, yep, with respect to the, oh, realized I did something stupid. Oops. That's a j, and that's a unit vector k. So this guy right here would represent q flux in the x direction, heat flux in the y direction, and heat flux in the z direction. Okay. So just, you know, keep in mind that you're only going to have heat conduction or heat transfer, heat conduction if you have a difference in temperature. So if there is no temperature gradient, if say dt dy, the temperature is, if that is equal to 0 because the temperature is not changing in that y direction, you don't have any heat transfer in that y direction. Another thing that I'll note is that this guy right here, even though he looks a little bit ugly, this has been made with one assumption, and that's that K is assumed to be constant, right? So in other words, you don't have a K defined in the X and the Y and the Z direction that are different from one another. That's outside of the scope of this class. All right, and I gave myself like 2 pieces of paper here for that, for just this little bit. But yeah, there we go. So I don't know, are y'all finished? I'm assuming so. I'll leave it for a minute though before I go on to the next guy.
I did have a question just while you're like waiting here.
Mm-hmm.
In the last problem, you had, you were able to say that, oh, okay, because it doesn't say otherwise, we can assume steady state. And then there was a problem yesterday where it ended up being that it wasn't steady state. And it was just kind of like we had to solve to determine whether or not it was. Can we assume, unless it asks us to find it or unless it says otherwise, that it is steady state for unit 1 at least?
Yes.
Okay, awesome.
Yes. Yeah, good question. Yeah. Had to throw in that one problem and then it messed it up. Yeah. All right. So let's move on to this guy. So we've got assuming steady state one-dimensional heat conduction through the shape shown below. So it's sort of like it's like a cone looking thing. This is the cross section of a cone, sort of a cone. So the little dots on the top and the bottom just indicate that around the perimeter there's insulation, so there's no, it's an adiabatic surface along the perimeter. And then assume E dot S, not E dot ST, E dot G, this is going to be equal to 0. But we want to find, and then of course it also said that it's steady state, right? Steady state 1D, okay, steady state 1D. It's pretty obvious, honestly, that it is one-dimensional because there's since this guy is insulated and this guy is insulated, there's not going to be conduction in the radial direction. It's only going to be in the x direction. But steady state, one-dimensional. We want to find T as a function of x. So we want to sketch the temperature distribution, and then we're going to explain it. We're just going to talk through it. How's that? And I guess I could have put those things that it said, assume this. Maybe I could have put that under assumptions, but it's okay. All right. So I guess the first thing that I'm going to do is I'm going to apply, don't like that. I'm going to apply a, there. I'm going to apply an energy balance. All right. And I'm going to apply an energy balance just on a little sliver here. So sliver here of thickness dx, okay? So let's call this x, and this is going to be x plus dx. Perfect. All right. Okay. So my energy balance on that control volume, well, let's go back. So I've got E dot ST is equal to any E dot in minus any E dot out plus our E dot G, which remember they just said in the upper left-hand corner, they said there is no energy generation. So this guy goes to 0. And they also said that it's steady state, which means that this E dot ST, which again is analogous to dE dt in your first law of thermo, this guy is going to go away as well. All right, so we've got, oh gosh. Got E dot in is equal to dot out. Okay. So then let's go over to our control volume again. So, well, what's going in and what's going out? Well, I have Q by conduction going in at X. And I know it's flowing in this direction because of the little statement to the right. It says T1 is bigger than T2. So this is T1, right? Some higher temperature. And then this guy over here is at a lower temperature. Right? So heat's going to be flowing from what's hotter to what's colder. All right. So I've got Q coming in at X, and then I've got Q coming out at X plus dx. And since that's all I've got, then I know that, okay, well, great. Q at X is equal to Q at X plus dx, which means that Q is just a constant. No matter what slice that I don't know why I'm putting that as a, no matter what slice I'm looking at, it's the same all the way through. Perfect. Okay. So the next thing I'm going to do is I'm going to look at, well, what's Fourier's law going to tell me? There we go. All right, so Fourier's law. So Fourier's law says that Q, and I'm gonna put it as, I'm gonna leave it as a heat transfer rate, but it's negative K A dt dx. So Q by conduction, negative K A dt dx, because it's only in the x direction. That's the only thing I have to worry about. And I know K is a constant. So I'm actually going to bring this dt dx, going to bring this over here. And so this is going to be negative Q over K. I'm going to kind of put that by itself. And then I've got 1 over A. And that's it, I guess. Okay. And then I'm going to take a step back, and I'm going to at least start plotting some points here. So t as a function of x on the y, and there's my x-axis. So if this is x equals L, all right, I'll have 2 temperatures that I'm looking at. I'll have the highest one, which is T1, and that's the temperature at x equals 0. And then I'm going to have T2, and that's going to be at x equals L. Now I got to figure out what goes on in between there, and that's where this guy is going to come in. So let's kind of look at what we've got here. So I know it's going to be decreasing. I got a negative sign here, right? So definitely going to be decreasing. This right here is a constant, and it's a negative constant, like we said, but it's a constant. I know it's a constant because I just figured out, okay, by my energy balance, it tells me that Q is a constant. With respect to X, K is a constant because it told me that there were constant properties. But then I got to look at the area. So the area is not increasing linearly with X because what we've got, remember, we've got this sort of like sort of cylinder that's kind of increasing, right? This sort of cone looking shape. And so it's not going to be a line connecting those 2 dots on my diagram over here, but it's going to be something else. So let's look at the area. So as x increases, area increases, and well, dt dx, as area is in the denominator, dt dx will decrease. So as we move from x is equal to 0 to x is equal to L, that slope dt dx is going to decrease. It's going to start out high, and then it's going to go down. So it should look, let's see what I could do here. There we go. So the slope's higher towards x equals 0, and then it kind of levels out. Not levels out, but just gets less steep. Let me know if you got questions about that guy.
Can you talk about that relationship again with like the as x as x increases?
Yes. So
the rest is I'm not quite there.
No, you're good. So as x is going, as you're moving from the left, you're moving from left to right. The area is increasing, right? And the area is the area that's perpendicular to flow. So it's that cross-sectional area there. I mean, that's not really pretty, but do you see what I'm saying? Like it's the cross-sectional area that heat is flowing through, because heat is flowing perpendicularly through it. So it's that cross-sectional area. And so that's getting bigger as you're moving from left to right. So that dt dx, which is the slope of this line right here. So the slope dt dx, as x gets bigger, as you move from this to this, the area is getting bigger, but because the area is on the bottom, the whole quantity is going to go down. So as you move from left to right, dt dx is going to get smaller. The slope is going to get less steep. The slope is going to get smaller.
Gotcha. Thank you.
Okay. So we got another one that's a little bit kind of similar. another one of these, like drawing your temperature distribution. Just so we have this one, the area, the cross-sectional area is the same all the way through. But what we have is we have different thermal conductivities. So we've got a section that's got a thermal conductivity of Ka. And you can see they tell us that this is half of Kb. So 0.5 Kb. And this guy is Kb. Then they tell us that T1 is less than T2. So this is just a little bit different in that on the left-hand side, you got the colder side, and on the right-hand side, you've got the hotter side. So you would expect, well, not that you would, you know that the heat is going to flow from what's hotter to what's cooler. So it's going to be going from right to left, your heat transfer, right? It's going to be going like that. And I could do kind of a similar thing. As I try to find what they're asking for. They want us to get the temperature distribution. Also, they want us to get this heat flux as a function of x. Okay, so that's fine. But I could do the same thing as far as, okay, well, let me apply an energy balance and see what I've got. Right. So E dot ST is equal to E dot in minus E dot out plus E dot G. If I look at the problem statement, it says that the thermal conductivity, okay, oh well, I got that. The thermal conductivity for A is half that of B. We want to sketch the steady state temperature and heat flux temperature distribution. Assume constant properties. Okay, so Ka is a constant, Kb is a constant, and no internal heat generation. So they did tell us that enough information to say that this guy is going to be 0. Perfect. Steady state temperature distribution. This guy goes away. So we're left with E dot in is equal to E dot out. And it's the same, it's going to be the same thing. If I kind of zero in on just a little segment here, and it doesn't really matter where I draw it, because that if I said this is x and this is x plus dx, all right, well, I've got q going in at x plus dx. Maybe I draw that in black because it's hard to see. So this is, you zoom in.
Would you draw that gradient in the opposite direction though, like x is on the right and x plus dx on the left?
No, just because they've already defined the coordinate system. So I'm just going with, this is in the direction of increasing x. Yeah. Yeah. But it won't really matter. So this is q at x plus dx. This guy is q at x. It don't matter. All that tells me is that q at x plus dx is equal to q at x, which is just some constant. Okay. Don't get hung up on the notation here. Down here, oh gosh. Down here, this q at x and q at x plus dx and q at x, I'm talking about a particular location. Over here, they're talking about just the general heat flux in the x direction. All right, so this is, Q in the x direction, the convective heat transfer in the x direction. All right. So I've written things in terms of heat transfer rates. I can also do the same thing with flux, right? So the heat flux in the x direction would be Q divided by the area. And since I know that the numerator, I just showed you that the numerator is constant, and we can see that the area, the cross-sectional area, is also constant. That means this is a constant, albeit a negative one, because it's going in the direction of decreasing x, right? It's going from right to left. So I guess I can really already do that part. So here's the function of x. And really, it's just going to be some negative number, but it's constant all the way through to x is equal to L. Pretty boring, right? It's just a negative number and it's constant no matter what x value you go to. All right. So that's part of it. That was half of the work. And now we got to find t as a function of x. So I'm going to apply Fourier's law. There we go. All right. So I know that Q, that heat flux, Fourier's law tells me it's K dt dx. Perfect. But I got to be careful because I've got two thermal conductivities. I've got one defined from 0 to 0.5 L and then 0.5 L to L. So might as well make sure I've got that. So for x equals 0 to x equals 0.5 L, then this would just be, and actually I'm going to rearrange it. I'm going to rearrange it because I'm ultimately looking for this dt dx. And that's going to be negative heat flux divided by K. So this will be dt dx is equal to negative Q heat flux, which is constant, over Ka. And then, of course, for the other one, for x equals 0.5 L to x equals L, it's going to be very similar. dt dx equals negative Q double prime over Kb. So Alex said, so the slope of, so I think you're just looking at this guy right here. All it's telling you is that this guy is a constant. It's a constant, right? So no matter at x equals 0, x equals 0.5 L, x equals L, it's equal to that qx that constant that we looked at. I feel like I'm gonna regret that. Yeah, the slope. Yeah, the slope doesn't really mean anything, right? Because it's just a constant. All right. Okay. So let's go to the temperature distribution now. Perfect. So our temperature distribution. So I've got T, the function of X. Here's X. And I'm going to do the same thing that I did before. I'm going to put a dot at X equals 0 and X is equal to L. So this is L and then X equals 0. And I've got two temperatures, right? I've got T2, which is over here. So T2 is the temperature on the right side. And T1 is the temperature on the left side. So the left side at X is equal to 0. So if we can kind of look here, that's this guy right here. So at X equals 0, that's the temperature. At X equals L, that's the temperature right here. And I just need to figure out like how they're related to one another in between. All right, and then I think probably maybe 0.5 L is probably a useful place to look at too. All right, so I know Ka is a constant and Kb is a constant. So that means this is a constant and this is a constant. But I remember that Ka it's smaller than Kb, right? Because Ka was equal to half of Kb. So if I'm looking at, okay, so if Ka is smaller, that means this is a bigger constant. Are we all okay with that? I think. Yeah, Ka is smaller. So from X equals 0 to X equals 0.5 L, that slope is bigger. So the slope is going to be sharper in the first half from 0 to 0.5 L. And so, yeah, let's see if I can draw it without making it look too ugly. There we go. Bigger constant, bigger slope. There we go. Okay. I'll leave it there just another hot minute. Okay. There we go. Okay. So let's go to problem 12. All right. So problem 12, we have a one-dimensional wall with thickness of 2L. Okay. So let's draw. Oh my goodness. Keep on hitting something apparently. So if we have a one-dimensional wall, I'm going to draw our wall here. Perfect. So it says that the wall has a thickness of 2L. And what they're trying to get us to do is to define our coordinate system like this. So this is X equals 0. This is X equals L, which would be not 0.05 meters, right? 50 millimeters. This would be negative L, X equals negative L. We'll talk in just a hot second about why that is, why it would be a good idea to do that. Oh, I did it again. And then it says we've got thermal energy generation of 1,000 watts per meter cubed. And I wanted to make sure that the nomenclature was clear. So this is a volumetric heat generation rate term, and it's in terms of watts per meter cubed. So it's not E dot G, it's E dot G per unit volume of this plane wall. So if I wanted to define, I'll actually put him down here. If I wanted to find that E dot G, it would be 1,000 watts per meter cubed times the volume of this whole wall. All right, so we'll talk about what that is, and it's convectively cooled at x equals plus or minus 50 millimeters, so plus or minus L, by an ambient fluid. So we have some fluid out here. This is at 20 degrees Celsius. This is at 20 degrees Celsius. Same H value, although we're not given what that H value is. That's actually something that we need to find. So we need to find the convective heat transfer coefficient. And we also, it's going to become apparent, we're going to need to find K to do this anyway. So I'm going to throw that on there as something that we need. So why does it make sense to define our coordinate system like that as opposed to, well, say the left-hand side is x equals 0? The reason is we're going to take advantage of what's called thermal symmetry. We look at what's going on with this plane wall. You've got energy generation such that the temperature in the middle is going to be the highest, and it's going to be lowest on the sides because you've got convective cooling going on. And so if I looked at, well, what does my temperature distribution actually look like? Well, it's actually, if I wanted to, so this is my midpoint. It's okay. So that's my, well, it's okay. But if I wanted to look at that temperature distribution, it would look something like this. Okay, so just trying to help us visualize it. So I'm going to zoom in on it so we can actually see it. So the temperature, so I've got that temperature distribution drawn with a little yellow dotted line there. So the temperature is highest in the middle. Makes sense because we've got volumetric heat generation going on, keeping it hot, keeping the temperature high at x equals 0, but you've got cooling on the sides pulling that temperature down. And because it's the same convective boundary condition on either side, you've got symmetry. And so what will happen is if you need to define, say, that temperature distribution, it's going to be the same temperature, well, or a mirror image temperature distribution on either side of that midpoint at x equals 0 or midplane. So why do we want to do this? Why is that important to recognize? It's because it makes the math easier. So if you don't recognize that, you've got thermal symmetry, it's fine. We could have defined this is x equals 0, this is x equals 2L, or 0.1 meter, 100 millimeters. That would have been fine. But maybe the math would have been a little bit more ugly. I don't think it would have been that bad, but yeah. So, okay. All right, so and it says, let's go back here. So it says, assume steady state conditions. Great. I was going to do that anyway. Oops. So assume steady state conditions. Perfect. And I think that's it. Oh, and then they also told us with the temperature distribution. Most of the time, we're not going to be given that information. But okay, now we're given it. Most of the time, it's going to be that temperature distribution is going to be something you are going to actually have to solve for. So, all right. And then A and B are constants, and I'll just I won't rewrite those. That's fine. All right, so I want to find H and K. So let's start by, so we're going to do an energy balance on the surface and on the control volume. Let's start with the surface, because if I look at that surface, well, I know that, just kind of thinking about what's going on, because I've got thermal energy generation and it's going to cause a temperature gradient within that medium. Temperature gradient in a solid substance is going to lead to conduction. So this is Q conduction. Oops. And then I've also got Q convection. Okay, perfect. So if I do a surface energy balance, and let's do that. Remember with a surface, and again, this is going to be my surface. A surface doesn't have volume, so there's no E dot ST, right? Because you need volume to store energy. There's no E dot gen, so that doesn't factor into it either because I'd have to have a volume associated with it. So a surface energy balance at X equals L, all that gives me is that E dot in, E dot out have to be the same. In other words, Q by conduction has to be equal to Q by convection. All right, Q by conduction, perfect. I've got, and actually, well, it's fine. So this would be negative K A dt dx, right? And this is dt dx at X equals L. I have to define that. And then that Q by convection is going to be H A times T at X equals L minus T infinity. All right, this area right here, that's A. That's the area that we're talking about. And so you can see it's the same on both sides. That it's going to go away. That dt dx, I actually have the temperature distribution, so perfect. So I just need to integrate this, or not integrate, but differentiate this guy right here. So A is a constant, L is a constant, B is a constant, so it's just going to be the derivative of negative AX squared. So I'm going to be left with negative K times negative 2AL, right? Because it's evaluated at X equals L, right? And then I've got H, and then I've got the temperature at X equals L. Well, if I look at my temperature distribution and I plug in L at X equals L, the temperature is going to be equal to B, and B is equal to 30 degrees. Is it supposed to be? Oh, you're good. Well, apparently I zoomed out for a hot second too. I'm sorry. Yep, that should be E dot out. Thank you. All right. So the temperature at X equals L is going to be equal to B. All right. So now we've got B minus T infinity. Yes, I know B is 30 degrees, and that's all well and good. Perfect. So if I look at what I know and what I don't know, I know L. Check. I know A, it's a constant. It's one of the things that was given to me. That's 10 degrees Celsius per meter squared. I'm given B, that was 30 degrees. I've got T infinity, that was 20 degrees. What I don't know is H and K. So I have two unknowns, one equation. Clearly I need another equation. All right, so we did a surface energy balance. Let's do a control volume energy balance and see what that gets us. Control energy, control volume energy balance. All right. So our control energy balance, we have, well, now I do have to take into consideration these two guys. So E dot ST is equal to E dot in minus E dot out plus my E dot G. All right, and let's look at our control volume, make sure that we're looking at, and we're thinking about the right thing. So it's this whole thing right there, that whole control volume. All right, they did tell me, they said that it's steady state, so I can at least get rid of that first one. So this is, oops, this guy's steady state. Why are you being annoying? There we go. Still being annoying. Okay. All right, so that term goes away. And then if I look at my control volume, I don't have anything coming in, right? So my control volume is this whole thing, right? I don't have anything going in. I just have things going out. I've got Q by convection going out. So that that E dot in term is going to be 0. That's too small. Yeah, this guy is going to be 0. So I have E dot G. Did it again. E dot G. And this is going to be equal to E dot out. And E dot out, well, it's equal to the Q by convection. But I have to make sure that I take into account the fact that I've got Q by convection on two sides. So yes, this is Q by convection. We'll note that that's got to be for two sides. All right. Now I need to start putting some other equations there. So my E dot G, it's 1,000 watts. Looking right here, 1,000 watts per meter cubed times the volume. So what's the volume? Well, the volume is that area, this area right here, that area times the width, which is 2L, right? So let's put that in there. I think I'm going to get rid of this, the colors, because it'll be confusing. But I've got,
scroll down
like this, like
yeah,
that.
like down. I can't see the bottom of the page.
Oh,
Wait, thank you.
Oh, is it because my name is on the way? Ow, it's annoying. How's that? I wish I could turn off my name.
That's good, thank you.
Okay. Alrighty, so my E dot G, so this is 1,000 watts per meter cubed times our volume, which we said was the area, times 2L. And now we've got the convection, and the convection happens on two sides. So by Newton's law of cooling, this is going to be the convective heat transfer coefficient times the area through which that convection happens, which is going to be 2A, since again, it's on both sides. And then it'll be T at x equals L minus T infinity. Remember this guy, T at x equals L. If we plugged things into our equation up there, T at x equals L is going to be B, which is 30 degrees.
Where does the A times 2L come from on the left side?
This is the volume. So this whole side needs to be in watts. This whole side, convection, needs to be in watts. So we need to make sure that the units work out. All right, so clearly the area, which we don't know, doesn't matter that we don't know it because it's going to get canceled out. So let's go ahead and bump it up. And actually that 2 goes away as well. So now we're left with H. We've got an H is equal to, so I have 1,000 watts per meter cubed times L, which is 0.05 meters, divided by T at X equals L, which again is 30 degrees, minus T infinity, which was, I forget already, 20 degrees. All right, so now we finally have enough information to get H. I've got 5 watts per meter squared Kelvin. So I'm going to box that. And now we can go back to that equation that we had before. And we can see that, okay, so K is going to be H times B minus T infinity over 2AL. So let's plug in some numbers. So I've got 5 watts per meter squared Kelvin times B, which...
Sorry, quick question.
Yeah.
Do we have to convert the 30 minus 20 degrees Celsius from 10 degrees Celsius to Kelvin? Since H is in meter squared Kelvin?
You don't. I mean, you can if you want to, but your delta temperature in Kelvin is going to be the same as delta T in degrees Celsius. So you can convert it, but you're going to get the same number. It's because it's the change in temperature.
Okay, thank you.
Yeah. Yep. All right, so we've got 30 degrees Celsius minus the 20 degrees Celsius on the top, and then we've got 2 times A. A was 10 degrees Celsius per meter squared. Yeah. Times L, which was 0.05 meters. I'm sorry, I'm sure that's hard to see. But you can see that what you're going to be left with, you should be left with a number, and I'm sorry I don't have it. Although, probably could figure that out. 2 times 1. Is that 50? Am I looking at that right? So you got 10 on the top, 10 on the bottom. That cancels out, and then you've got 0.1. So it's 5 divided by 0.1. That's 50, right? I'll take the silences. Yep, that's it. All right. Perfect. All right, so let's go. Let's at least start talking about the Cartesian the heat generation equation in Cartesian coordinates. This is actually as far as we got this morning, and I don't want to get too far off from where we got this morning, but I do want to at least go a little bit, just a tiny bit further, if that's okay. All right. So this one is kind of a loaded video, that video 2.3, but it's your heat diffusion equation. And the heat diffusion equation is just a glorified energy balance, but it makes it prettier. So I'm going to rearrange that energy balance, if you don't mind. I'm going to put my E dot in minus E dot out. Okay, so there's that one. I'll put him in green. And I'll put my dot G, I'll put him in purple. And let's too ugly. Let's put the other one in orange. So this is E dot ST. All right, so video 2.3 walks through the derivation of how we start with this very general form of the control of the energy balance for that control volume. And now, by the way, I'm gonna so it talks about how we take that very general form and get what's called our heat diffusion or heat conduction equation, which again, it's just a glorified energy balance. That's it. All right, so it's going to look like this. We've got the second partial derivative of the temperature with respect to x plus same thing, second partial with respect to y plus second partial with respect to z. All right, and so you can see, unless you're colorblind, this guy and this guy are related to one another. Right? It's not the exact same, but it's the terms are related to one another. So that first one is the net rate or the related to the net rate of heat conduction into the medium, plus the rate of energy generation. And so we're going to define this term right here. So Q dot over K. Q dot is the volumetric heat generation in terms of energy per unit volume. So in SI units, it'd be watts per meter cubed. All right. And then we've got the final term, the E dot ST. So it's 1 over this guy right here. That's not the absorptivity that we talked about at the beginning. This is the thermal diffusivity. I know it's still an alpha, but just it's different. So this guy is the thermal diffusivity. Again, not related to the absorptivity, which we talked about when we talked about radiation, or irradiation rather, and the amount of radiation that's absorbed by the surface. This guy is defined as K over rho Cp. So Cp, specific heat, hopefully you're familiar with that. So specific heat is it's a property, it's a material property. It's the amount of energy that you have to put into the substance to increase the temperature by 1 degree, either 1 degree Celsius or 1 Kelvin, but 1 unit degree. K is the thermal conductivity, which we talked about. So what this is this is really just kind of a measure. If you think about, like, okay, well, what does that number really mean? It's going to be a measure of how well a material conducts thermal energy over a measure. I'm kind of using my little hash marks to say it's a measure of how well that material is able to store thermal energy. All right. All right. Perfect. All right, so that's our heat diffusion equation. And if you're worried about having to memorize it, don't be. It's on your equation sheet. And we'll look at it in a hot second and see what that looks like. See where that is. Okay, perfect. So if you look on the upper right hand side, you see you have the heat diffusion or heat conduction equation. You've got it in Cartesian coordinates. You also have it in cylindrical coordinates, so there's not really a need to memorize it. Just be familiar with what those terms represent. So let's just kind of look at it. If it was steady state, if you had steady state heat conduction, one dimensional, say in the x direction, and no heat generation, well, then that equation gets really simple really quickly, doesn't it? It'll just become partial of t with respect to x equals 0. And in that case, well, you don't need a partial anymore because it's only dependent, temperature is only dependent on x. So you could really just get rid of that partial and just regular old second derivative dt dx. So the units for thermal diffusivity, well, per second, I think. Well, let's think about it. So K is in watts. Watts per, not meters squared, watts per meter Kelvin. And then we've got, I'll delete this guy. And then we've got rho, which would be, oops, I'm so sorry. Watts are in turn, stop it. Watts are in units of oh wow, that was difficult to pull out. Kilograms per meter cubed. And then your CP would be in terms of watts. So joules per kilogram K. Okay. So let's see if we can figure that out. So we're Kelvin, kilograms are going to go away. So we have this meter and that one goes away. Feel like I got something.
Is it meters squared per second?
It is. It is. I'm wanting to know why my second is not on the right thing. It's not on the right because it's ending up in the wrong place. So I'll have meters squared on the top. Ah.
Is it because it's 1 over thermal efficiency or diffusivity?
No, it's so CP is going to be, it's a joule. It's not a second. Yes, I'm sorry. It's this guy. That guy. That should be, and it's also, oops. It's also this guy. There we go. So your watt up on the top is going to be a joule per second. Finally. Joule, joule. There we go. Now it's in the right place. Yeah, so now we've got meter squared per second. My goodness. Yeah. Sorry. All right, are we not concerned with the DT? Are we not concerned with the DT, the derivative of temperature with respect to time multiplied by 1 over the thermal diffusivity? It's the same on the equation sheet as what we just wrote, I think, right? Ah! We are concerned about it. Thank you. Maybe I should have stopped while I was ahead. Thank you. There we go. There we go. Thank you, Blake. All right. Should we do one more problem? Let's do one more problem, and then I'll just kind of open it up to if you have any questions. I think that'll be good. And the problem will be pretty short, so don't worry about that. All right, so problem 13. It says starting with the three-dimensional heat conduction equation, write down the 1D transient heat conduction equation for a plane wall with constant thermal conductivity. Plane wall with constant thermal conductivity and heat generation in its simplest form. Okay, so easy peasy. So we have a plane wall. There's our plane wall. Said we do have heat generation. So, or we don't have heat generation. No, we do. Yeah. So we have a Q dot. Okay, fine. All right, so it's transient, so I can't really get rid of the DT, derivative, first derivative temperature with respect to time. So writing down our equation here. So we have the second partial derivative of temperature with respect to x, with respect to y, and with respect to z, plus q dot over k, and that's going to be equal to 1 over the thermal diffusivity times the partial derivative of temperature with respect to time. Good gracious. All right. So it says transient, so I don't want to get rid of that last term. Can't get rid of that. I do have heat generation, so I can't get rid of the term in purple, but it does say I have one-dimensional heat transfer. So I'm going to throw in here that it's 1D in the x direction. So I'll just cross these guys out, and that's kind of all I can do. Everything else just has to stay there since it's transient and we have heat conduction. So that would be it. So all I'm doing is finding, I'm not asking to solve for it. Yeah. So next time, we'll talk about boundary conditions. So talk about applying boundary conditions. And actually solving the heat diffusion equation. For this unit right here, it's all going to be steady state. Just be aware of that. It'll all be steady state and one dimensional. We'll introduce 2 dimensions, I think, in unit 2. All right, so I'll stop there. If you do have questions, please let me know. But other than that, thanks for especially those people that paid attention and caught when I made an error. Thank you for that.
Thank you.
All right. Number 10? Yeah, sure. 12, 11. Goodness. There we go. All right, Seda.
Okay, I'm good. Thank you.
Okay, yep. All right, Josh, I'll go back for you. Maybe this stuff right there. Thank you, guys. So I'm gonna turn my camera off just so my face is out of the way.